So, welcome to this class on hardware security. So, we shall be continuing and finishing off our discussion on how to guess or estimate the number of power traces to estimate the statistical parameters which are required for a difference of mean attack. So, we will be basically like we were in the last class, we were discussing about this equation. So, we were basically trying to estimate the number of observations which are required to estimate mu properly. So, if you remember right, what we are saying is that we have essentially a like a standard normal distribution in which we are trying to we are basically through which we are trying to use its quantiles to kind of estimate the mu which is there in our normal in our normal distribution. So, we are basically transforming that into a z statistic, and from there we are trying to estimate that. The idea was that if you have got, if you want to like estimate the mean with precision c. So, this c could be say 0.01 or 0.001, that depends upon the amount of accuracy that you would like. So, if I want therefore right, I mean essentially alpha, as we discussed in the last class is our error probability, and that means that we have got a standard normal distribution, and let me just draw it once more. So, you have got this as your standard normal distribution, and you are basically trying to estimate the mu, right. So, the idea is that if your z statistic is like given more than a specific value, that means if you are basically trying, if your estimate of mu is given as x bar, because you do not know what is the actual value of mu, and you find out the error. So, this is your error, right, because you are trying to estimate whether the mean is equal to mu naught, and so therefore, the null hypothesis that you are considering is mu is equal to mu naught, and the alternative hypothesis is mu is not equal to mu naught, but you do not know mu naught, right. So, you are basically trying to estimate. So, you actually know mu naught, but you do not know what is the value of mu. Okay. So, you are basically trying to estimate it by this parameter x bar. So, the idea is that if this particular value, that is x bar minus mu naught, the absolute value of this is greater than c, right, then that is an error. Okay. So, we are basically trying to find out the probability that, so you know that this probability is equal to alpha. So, now from here we basically tried to derive this equation which we derived in the last class, and we got this as a corresponding estimate. Okay. That is, n is given by sigma square by c square into z 1 minus alpha by 2 whole square. But often when we analyze power attacks, we do not like need to actually estimate the value of the mean, but what we rather require is to estimate whether the means are different or whether the means are same. Okay. Or we need to kind of estimate whether the mean is say less than 0 or the mean is greater than 0. Okay. So, we basically need to estimate the mean is say equal to 0 or the mean is not equal to 0. Okay. So, therefore, right, we probably need to do an so this is another kind of problem, right, which we need to also kind of solve. So, we basically are trying to kind of analyze this fact that p of say x bar, okay, which is your estimated mean, whether this is lesser than equal to 0, and we know that we are as we know that this probability, right, is equal to 1 minus alpha. Okay. So, we are basically trying to say that with a good amount of confidence, and the confidence is 1 minus alpha, we are trying to find out the probability that x bar is lesser than 0. Suppose your mean is negative. Okay. So, this is given that the mean or mu equal to mu naught, okay, with mu naught lesser than 0. So, in this case the mean is a negative value. Okay. So, that means, right, if you observe the corresponding, so we can basically rewrite this inequation by like just writing x bar minus mu into root n by sigma, and writing that this is lesser than equal to minus mu root n by sigma. Okay. That is basically just I am writing x bar, I am deducting a minus mu from both sides. So, I get minus mu, and then I multiply by root n by sigma. Again note that sigma is positive. So, therefore, if I multiply, then the signs do not change. Okay. So, this probability, right, essentially remains the same, and essentially is also equal to 1 minus alpha. Okay. So, that means, right, this part essentially is nothing but my z statistic, which essentially follows a standard normal distribution. So, essentially the mean is 0 and sigma is 1. Okay. This is what we have already seen in the last class. Okay. So, that means right this we can write it as P z is lesser than minus mu into root of n by sigma. Okay. And that is nothing but the cumulative frequency at the point or few like phi evaluated at minus mu root of n by sigma. Okay. And so, that means right if you remember right we said that so this is equal to 1 minus alpha. Okay. And we discussed right therefore, that this parameter okay, that is minus mu root of n by sigma is nothing but z 1 minus alpha. Okay. Right, because as we define right that phi of z alpha is equal to alpha. Okay. So, that means phi of z 1 minus alpha is equal to 1 minus alpha. Right. So, therefore, we have got this and note that your mean or mu right is essentially negative. Okay, and therefore, what you essentially have is this equation. Okay. So, now from here I can estimate by squaring. So, if I square I will get mu square into n divided by sigma square and that is equal to z 1 minus alpha square, or we basically get n is equal to sigma square by mu square into z 1 minus alpha square. Okay. So, this is a different equation than what we got because our objective is different. Okay. And very often you may find that this n is probably much lesser than the previous value of n. Okay. And you can try to like use some possible values and from there you can try to experiment that whether that ordering is true or not, okay, which I leave it to as an exercise. So, therefore, right I mean with this background right we can now get back again to our discussion and continue. Okay. So, therefore, right this is what I just wanted to show is that this number of trace right depends upon the hypothesis, and it is not that whatever hypothesis you make this is the number of observations required. Okay. It will depend upon your hypothesis. So, you need to do a case by case analysis. Okay. So, it is interesting how you derive them and depending upon the hypothesis which you make. Okay. So, therefore, right we are now almost set to estimate the number of traces which I need for estimating the difference of mean. So, now we have got two like distributions. Okay. So, we have got a distribution 0 and we have got a distribution 1, right. So, we have got in our difference of mean attack we are essentially having two bins. So, we have a 0 bin and we have a 1 bin, right. So, what we do is we are basically having our encryption algorithm. So, let me call this as an AES round for example. Okay. And in the final operation right you basically do an exclusive OR with your 10th round key for example, if you are talking about AES 128, and this is the corresponding cipher which you are generating. Okay. So, what you are doing as an attacker is that from this key you are basically guessing only a portion of this key, right, and then you are basically targeting say the last round say one of the S boxes here. Okay. So, you are basically like inverting this S box going to a specific bit, and if this bit right depending upon your guess here, that is the guess that you make for this key byte is whether this according to this guess you get a 0 value here or you get a 1 value here from the ciphertext. So, you basically take the ciphertext, you XOR with the key, you take the inverse S box and you go to that target bit, right, and depending upon whether the target bit is 0 or 1 you put the power trace into the 0 bin or you put the power trace into the 1 bin. So, now we have got two statistical distributions, one distribution say let me call it x and the other distribution is what we have called as y. Okay. So, x actually follows a normal distribution. So, this normal distribution is essentially say mu x comma sigma, and y essentially follows also another normal distribution, say denoted as mu y and sigma. Okay. So, note that I have kept the sigma same in both the cases, which is most likely to happen. Okay, although there may be small differences, in that case I will probably substitute by an average sigma, okay, because they are roughly the same, because they are taken from the same population and likely they would be same. So, I am just tacitly assuming that they are same, okay, for simplicity of our analysis. So, therefore, now the interesting thing is that what we need is to estimate this distribution or x bar minus y bar. That is, you see that I have taken the sampling distribution of the average of this distribution, I have taken the sampling distribution of the average of this distribution, and then I am considering the difference of them. Okay. So, that is denoted as x bar minus y bar. This will also follow a normal distribution, where the mean will get reduced, the mean will get subtracted mu x minus mu y, but the interesting thing is that the variance will get added up. Okay. So, for example, like if the sigma, in this case I have assumed that both the traces have got same number of values, okay, same number of samples. If it is not the same, then you can probably throw away some samples and make it same, okay. But if you are also, but you can also generalize it, like if you say that this has got say m traces and this has got say n traces, then this sigma would be sigma square root of m plus n divided by m n. Okay. So, if I substitute m and n as same, then basically you have got sigma into square root of n plus n divided by 2n. Okay. And this means that it is essentially I mean it basically, so it is basically n plus n divided by n squared. So, maybe you should correct it actually, this is n plus n by n squared. Okay. So, that means it is square root of 2n divided by n squared, and that is equal to nothing but square root of 2 by n. Okay. And that is essentially this denominator factor, which is essentially sigma square root of 2 by n. And now if I make a transformation, that is I basically take x bar minus y bar and I subtract out the mean of this distribution, which is minus mu x minus mu y, and divided by sigma square root of 2 by n, which is the standard deviation of this distribution, then as expected, like what we discussed before, we get a standard normal distribution. Okay. So, now we will try to play around with this z and again develop the confidence intervals for mu x minus mu y. Okay. So, because that is what we want to estimate. Okay. So, therefore, I mean so with this background, let us see how we can do that. So, we basically try to or want to derive the confidence interval for difference of mean, that is our objective. The confidence interval for mu x minus mu y for a known sigma, therefore, you can derive from this confidence interval for z, right. So, the confidence interval for z, as we discussed in the previous class, was from z alpha by 2 to z 1 minus alpha by 2. Okay. And now, we make again this substitution that z essentially is nothing but this, that is x bar minus y bar minus mu x minus mu y divided by sigma square root of 2 by n. Now, note that in this, so basically if we make a hypothesis that so basically if you make, so what we do is that, I mean if the corresponding confidence interval for mu x minus mu y, in that case will be x bar minus y bar minus, or you can say x bar minus y bar plus minus sigma by square root of this would be 2 by n actually. Okay. So, maybe again you should make another correction, which is that this is square root of 2 by n. Okay. So, square root of 2 by n, so plus minus sigma by square root of 2 by n z 1 minus alpha by 2. Okay. So, now we make a null hypothesis. The null hypothesis is essentially that mu x minus mu y is equal to 0, which means that both the means are same. The alternative hypothesis is that mu x minus mu y is not equal to 0. Okay. So, therefore, we test this statistic z. So, note that here I have assumed the null hypothesis. So, therefore, mu x minus mu y is 0, and therefore, I test that if z is equal to x bar minus y bar divided by sigma square root of 2 by n, whether this lies in the critical region. Okay. So, the critical region is essentially as previously depicted. So, you can again apply the same technique. So, what you basically have got is 2 times the probability that x bar minus y bar by sigma square root of 2 by n, that is this value, is basically greater than c by sigma square root of 2 sigma square root of 2 by n. So, that means that x bar minus y bar is exceeding c. Okay. And that is c is essentially the precision or the tolerance which you are allowing. Okay. So, therefore, right, if I set this as alpha, because this is essentially alpha in this case, that means that this parameter, that is c by sigma square root of 2 by n, is nothing but z 1 minus alpha by 2, as we have previously discussed, and therefore, now the number of traces can be obtained by this formula. So, n is equal to 2 times sigma square by c square into z 1 minus alpha by 2 whole square. Okay. So, therefore, right, again, right, with this equation, so now we will be trying to utilize this in an actual experimental setting. Okay. So, therefore, right, let us see this case study. So, this case study shows how you are. So, we are again trying to perform a difference of mean attack on the last round of AES. Okay. So, in the last round of AES, again we have got two distributions because of the 0 bin and the 1 bin that I talked about. So, suppose this is your normal distribution, I mean the fitted normal distribution for one of the sets, I call that as set A for example, and this is the sampling distribution for mean. Okay. So, note that the variance essentially has got reduced, okay, and that is essentially expected, right, because the variance should get like sigma by square root of n. So, therefore, you need to get a narrow normal distribution. Okay. And likewise, right, for the other bin you have this normal distribution, and if you again apply or obtain the sampling distribution for the mean, you again obtain another set which is again narrow. Okay. So, therefore, the set A refers to target bit 0 and set B refers to target bit being 1. Okay. The target bit, this is the same target bit, but sometimes it takes the value of 0 and sometimes it takes the value of 1. Okay. So, now we observe that these are my sampling distributions, that so that means that this is your x bar set and this is your y bar set. Okay. These are the sampling distributions for the mean which belongs to set A, and this is the sampling distribution for the set B or the mean of set B. So, now what we just discussed here, that you essentially you take one of these difference of mean plots. So, this is the difference of mean plot. So, observe the difference of mean now takes a nice normal distribution. Okay. So, the difference of distribution means that you have got all these averages, and you are basically trying to take the difference of these averages. Okay. So, you are taking you are taking an average from one set, you are taking the average from the other set, and you are computing their differences. So, this difference, right, as we discussed, that x bar minus y bar also follows a normal distribution, and this is how it looks like in our case. Okay. So, this is a normal distribution. If you want to standardize it, again you can apply the standardization technique, and this is the corresponding standard normal distribution curve. Okay. So, now the final thing, we want to estimate the number of traces which are required. So, what we do is that we observe here around 4296 traces with roughly equal proportions going to set x and set y. For our analysis, we have discarded some cases where like there are aberrations and things like that. We have discarded few cases where we had inequality in these two sets. So, that finally, we have got two sets with roughly the same number of samples, and the sigma, it turns out to be 0.07. Again, the sigma was not exactly 7. So, we kind of approximated by the average, they were almost same. So, we approximated by the average sigma, and we set a c value of 0.01, that is the accuracy that I allow. Okay. That means mu x minus mu y is equal to 0 is my null hypothesis. I allow a small tolerance of say 0.01, that means it can be 0.01 above 0, okay, above or below 0. So, therefore, right, for a confidence of, suppose I set a confidence of 0.95, suppose somebody asks you that you should guess this with a confidence of 0.95, that means 1 minus alpha is 0.95, right. That implies that alpha is equal to 0.05, and that means 1 minus alpha by 2 is equal to 0.975, right. So, therefore, you should find out the quantile at z 0.975, and if you refer back to the table that we saw, the corresponding entry over there was 1.96. Okay. So, therefore, right, this is my corresponding value here 1.96. So, therefore, if I just plug in here to my equation, which is essentially given in the previous discussion, that is n is equal to 2 sigma squared by c squared into z 1 minus alpha by 2 whole square. So, we just plug in these values here to get 2 into 0.07 squared by 0.01 squared into 1.96 squared, and this works out to 377. Okay. So, again this is a rough approximation, but like you get a rough estimate that the number of traces which are required to indeed understand or accept the null hypothesis with a reasonably high confidence. Okay. So, if you are accepting the null hypothesis, right, then what does it mean? it means that mu x minus mu y is roughly equal to 0. So, in which case will it correspond to the wrong guess or the correct guess? It will correspond to the wrong guess, because in the wrong case both the bins, right, will have the same average or similar averages. But if you are doing it for the correct case, right, where you are basically kind of rejecting the null hypothesis, those are your candidate kits. Okay. So, that is exactly what we will do in our attack. So, what we do in our attack is basically we carry on the attack eventually, and you can observe that, as I said, that we are targeting the last round of AES. So, these are all the rounds that we have targeted. So, this is the corresponding, like the samples that we have observed, and the red are essentially, the red color has been used to indicate the wrong guesses and the blue for the correct one, and you can see that the difference of mean for the correct, right, essentially is kind of strikingly distinct from the wrong ones. Okay, and you essentially are able to distinguish the correct one, the correct key guess from the wrong key guesses. Okay. So, this roughly corresponds to the last part of your cipher, where you are doing the last round of your encryption. So, this is the reference that we have followed. So, of course, we have followed our standard textbook, but this is also another very nice textbook which you can refer to. It is written by Stefan Mangard, Elizabeth Oswald, Thomas Pope. It is called Power Analysis Attacks Revealing the Secrets of Smart Cards. This is published by Springer. So, to conclude, what we discussed is DPA setup is crucial to the success of DPA. Noise is an integral component of power traces, and therefore, you need to properly analyze noise. The noise can be of two types. It can be of electrical noise, it can be algorithmic noise. As we discussed, the algorithmic noise also has got influence on the algorithm, on the architecture. Like if we will see later on how we can compare a parallel architecture with a serialized architecture with respect to algorithmic noise. The electrical noise is more fundamental and depends upon the platform, okay, but at the same time we would like to reduce the electrical noise by applying proper insulations and proper and using proper probes for communicating the power signal from your target to the oscilloscope. And DPA, right, is largely based on statistical theory. So, it is important to kind of go back and look at these techniques which are like hypothesis testing and so on, which can help in estimating the number of observations which are required for like guessing properly the parameters which are needed to do an attack with high confidence. Okay. So, it is always good to back up our experiments with a good rational and proper explanations using statistical tools. Okay. And these statistical tools which we just now discussed help us in doing so. Okay. So, with that I would like to thank you for your attention.